Okay, go.
So for your negative sign, the only thing that I could see was that they were evaluating just differently from you. So I mean, if you're doing it your way, then you're right.
Well, yeah.
Their way.
The thing is, if you look at, basically what we did is right, and it's just the way the book gets rid of their minus sign. Mm-hmm. They just don't explain that. It's kind of hand wavy, but it's accurate. They just don't explain themselves. So equation 23.17 in the book, it says VA minus VB. Let me just erase this and write. So they say VA minus VB equals the integral from A to B of E dot dr, whatever. But if we replace these with, so if I called this delta V, right? And we always say that that's V final minus V initial. They called that V final as A, and they called V initial as B. And so down here, they've got final minus initial. Whereas normally when we integrate, we go from initial to final. So this is the same thing as saying minus the integral of initial to final, or, B to A, of E dot dr. So they got rid of the minus sign. They did it accurately, they just don't explain themselves. And so if we look back to this problem we did here, my delta V is VB minus VA. And if you just replace that with VA minus VB, then you can get rid of the minus sign. And so everything we've done so far is accurate. And if you just decide to switch, you say instead of saying delta V is VB minus VA, and you make it the reverse of that, then you can put a minus sign out front. And that's all the book is doing. They just never explain themselves. Yeah.
So like for an answer, how would you have to explicitly define what delta V is then?
I think that would help. I think it's helpful to say VA minus VB equals plus, because of this point of confusion that we have, that it's explicit, so we know exactly which direction we're going. Because this is V final minus V initial, so I mean, when we drew it, we did this is initial and this is final. And then the way the book is doing it is there. I mean, it's what we said before. We said, that the trick was to always integrate backwards. And so we did that on the first two examples explicitly. This example, we just followed the book's method. But that's what they're doing. They just don't say that's what they're doing. And I like to be a little bit more explicit in my explanations. So, but yeah, going back to your question, Hannah, I think it would help to just say, if you write what the delta V is in terms of which direction you went, that way we know, or you can remember later on. Yeah, I mean, you probably won't be doing a lot of integrating on your homework. We're going to take, well, I can't say that for sure, but
you would figure that'd be nightmarish on you. You'd have to see how we're integrating.
Yeah, I mean, I think I can't say this for sure. I have to check, but typically we do a lot of the integrating in class, and then you can use the results on your homework. Because I don't know, like I don't need to test your calculus skills. Presumably you went through that already in a calculus class. So, but before I say that, I'm just going to check that you don't have integrals on your homework. Oh, there's an integral. Problem 2315, there was an integral, but that was work, not potential energy. And problem 2349 uses this result, so you don't have to rederive it. You can just use this result. Okay, yeah. So you have one integral that shows up on your homework, and it's a work integral. So this whole business, this funny business, won't come up. Yeah. And I will make sure that, I don't ever put integrals on your test, so I can promise you, you won't have to deal with this funny business on the test.
Awesome.
So, all right. Okay, so where were we? Let's go back to whichever slide we ended on. Okay, this was the last slide we ended on. So the next topic is equipotentials and conductors. So this is kind of working our way towards capacitors. That's what we're going to finish with today. So when all charges are at rest, the surface of a conductor is always an equipotential surface. That means that the voltage at all points on that surface are the same. The electric field just outside the conductor is always perpendicular to the surface, which we talked about at the beginning of the class when I drew that weird potato-y shape. And I said, draw the electric field lines, and we're kind of like, well, how would we do that? And I said, all we have to know is that the electric field is always perpendicular to that surface at all points. So that's that point. And then because the conductor has a zero electric field on the inside, we said the change in potential on the inside is zero. Therefore, there's my therefore symbol, the potential at any point on the inside would be constant. All right, so just reestablishing things we've already covered. So chapter 24, capacitance and dielectrics. Capacitors. So anybody, well, actually, you know what? On this sign-in sheet, I'm going to add a little column. I don't know that I asked you this the first day. Did I? I did. Never mind. Okay. Thanks, Hannah. So just remind me again, yeah, just by a show of hands, who's taken circuits in here? All right, good. Nice distribution. So when we do circuit labs, distribute yourselves in groups so that we don't end up with one group who've done circuits and finish in 10 minutes and everybody else taking 2 hours, because you guys will be sort of helpful at assisting students who haven't had circuits. So this is like our first inkling of actual circuits. So we're talking about things that you can plug into a circuit and then they have some kind of functionality. So a capacitor. A capacitor is a device where we can store energy, and presumably, I mean, we usually assume that the capacitor stores energy indefinitely. We know in the real world that is not true. Yeah, it's going to decay over time. If it was true, then every neighborhood could have a mini substation of giant capacitors that could just store energy, and then we would have no energy crisis. We would always be green in Oregon because in the summer, Bonneville is running at full steam. We're making so much energy, we sell it to all the states around us because it's so, there's too much to be used. So if we could store that and have it sit around indefinitely, we could be using Bonneville power year round, and then we would be green. We'd never have to use a coal power plant. It would be great. Unfortunately, that's not the real world. But in physics land, where we like to make approximations, we're going to assume that our capacitors hold their charge indefinitely. Okay, so that's kind of what they do. So they're kind of like a battery in that way. They can hold their charge until you need it, and then you can take out that charge later and do something with it. So some things that use capacitors: the camera flash on your phone, pulse lasers, your airbag sensor, radio and TV receivers. Any circuit is going to have a capacitor. Any complicated circuit, that shows up in your computer or something is going to have a capacitor in it.
Does the airbag sensor use a capacitor?
I don't know. Not off the top of my head. My guess is that they measure for some change in potential difference or something. Like you have a circuit that has a certain potential difference, and then the impact or some kind of impact thing can trigger a change in that potential difference. Yeah. Okay, so capacitors use symbol capital C, and this is the symbol we use in a circuit. And so the capacitor is the device in a circuit. And a capacitor can be measured by its capacitance. So capacitance is sort of a quantity rating your capacitor. And so it has the same symbol, because otherwise that would be confusing. And we'll talk about on the next slide what capacitance is, but just for summary here, the units of capacitance is farads. We use symbol F for farads. That comes from Michael Faraday. All right, and this symbol, we're also going to talk about why we use this symbol in particular coming up. All right, so any two conductors. So this picture just shows like an amorphous blob of metal, another amorphous blob of metal. One has positive Q charge sitting on it, the other has negative Q sitting on it. We know that's going to create this electric field. So any two conductors that have equal and opposite charge form a capacitor. And we call these two conductors plates. That seems weird when they're these weird amorphous blobs, but if you instead actually have a sheet of metal and another sheet of metal, then that looks a whole lot more like a plate. And that's where this drawing comes from. That's like the cross section of two plates. And so between them is a gap of air. Right now it's air. When we talk about dielectrics, that would be what we put inside between the plates is dielectric material. So what defines how much charge these plates can hold? What do you think defines how much charge it can hold? The area? Yeah. So the size of that plate. Imagine, we talked about charge per unit length or charge per unit area. The bigger the area, the more charges you could carry. The other thing that dictates the capacitance. Yeah.
The air resistance, right?
Yeah, so the gap between them, the air that's between them is actually limiting how much electric field you can have. So that the smaller that air gap, the more capacitance you can have. So that's the key thing. We want to make this gap between the plates as small as possible. But it's a positive and a negative plate. So what are they trying to do? Yeah, they want to go together. And so if there was an air gap, it would be really hard to get these two plates super close together without them wanting to touch. And then your electric field goes away if they touch. So that's actually the actual benefit of a dielectric, is you have something that separates the plates. And you can make that material really, really thin so the separation is very, very small and they can't bridge together. Oh, not yet. I was going to say, and this is the formula for capacitance. I guess we're not there yet. Okay, so so this slide we're going to talk about what a capacitor does when you put it in a circuit. So this is about the most basic circuit you can have, where you hook up a capacitor to a battery. So this is our symbol for a battery. Actually, I'm just going to erase this for now. So battery in a circuit looks like this. It's got a short and a long side. It sometimes looks just like that. Sometimes it looks like this with a plus side on the long plate and a negative on the short plate. Sometimes they'll just get rid of the negative sign. And if you've got multiple batteries together, like your TV remote, it's got like 2 or 3 batteries in there, then it looks like this if you had 2 batteries, or it could have a plus sign. So all of these just mean battery. That's all that you need to know. Those are all symbols for batteries. So the battery has a plus side and a minus side. What a battery does similar to what a capacitor does, is it stores energy that can be used later. And it does that by way of some chemical reaction, and so it's able to create a potential difference between its plus and a minus side. So there's a potential difference here, and so the top side of the battery has positive charges that collect on it. And so if you put a wire that connects that top plate to one side of a capacitor, then the negatives, the electrons, it's a conductor, right? And the wire is a conductor. So the electrons want to move, and they'll move towards this positive side, since electrons are attracted to a positive side. So if a bunch of electrons leave this top plate to go to the battery, what does that leave on the top plate? Positives, yeah. If a bunch of electrons leave, we're left with the positive plate on the top. That positive plate is going to attract electrons. Those electrons actually come from the negative side of the battery. So the negative plate, or the bottom plate, collects a bunch of electrons so that you have an equal number of positives and negatives on the top and the bottom of the capacitor plates. So once that happens, you build up this electric field. And that electric field is based on how many charges collect on the top and bottom plate. The number of charges that build up on the top and bottom plate is directly related to the size of this battery. So our electric field, so the battery has some potential difference. So what we measure that as, you grab your 1.5 volt AA battery, that's the potential difference. So from the negative terminal to the positive terminal, you have an increase of 1.5 volts. So that delta V equals E times the distance between the plates. So this, where that came from, if you plug in, we could go through the integral all the way. You know, delta V is minus the integral of E cosine ds. This is the distance between the capacitor plates. Need our theta here. If we integrate from the bottom plate to the top plate, so in the opposite direction of the electric field, we get cosine of 180. So that term goes to -1, cancels the minus out front. So we have plus, and then the electric field is constant between these two plates because the lines are straight, so it's not changing. So we pull the E out of the integral, and we're just integrating ds. And so the integral of ds is S. So S is the distance between the plates, and just for consistency with our next slide, we actually call that distance D, but that would be weird because then we'd have DD. That looks weird. So I'm just gonna call it D now. Okay. So the voltage of the battery directly impacts the electric field that builds up on those capacitor plates. Okay. Okay, now we'll talk about capacitance. Okay, so the definition of capacitance is the ability of a capacitor to store a given amount of charge. As we predicted, it depends on the geometry of the plates and the distance between the plates. So a farad, that's the units, can be broken down into a coulomb per volt. So that helps us come up with one definition for capacitance of charge over the potential difference of the battery. So the slide has it written as Q is equal to C delta V. So either of those is fine. Here's some other useful things on here. Usually capacitors are in terms of microfarads or picofarads because 1 farad is huge. So this is our conversion. If you just want to make note, a micro is 10 to the minus 6, pico is 10 to the minus 12th. So if you wanted to figure out what the charge built up on those plates is, you can use Gauss's law to derive that. So this is walking through Gauss's law, and we get that Q enclosed is E naught, the electric field times the area of the plate. So I'll put that over here. Okay, and then we can combine those two equations and this definition that we just derived, that the potential difference of the battery dictates the size of the electric field. And I don't know why that's all wonky. Okay, so combining those two equations, the Q equals C delta V and delta V is E over D, we can derive an expression for capacitance that's relating to the size of the plates and the distance between them. So there's a derivation up there. Our take-home message is C is equal to E naught A over D. Area of the plate. Okay. So real capacitors, I don't think this comes up in our presentation, but real capacitors are not a flat plate like that because that would take up a lot of space. And so what they actually do is they'll make a plate, and they can't do this unless there's dielectric between the plates. Otherwise, you'd end up with the plates smushing together. So they'll put a dielectric between the plates. Dielectrics are usually made out of plastic. And then they roll the whole thing up. And it works the same way even when it's rolled up. And so capacitors in actual circuits look a lot like this. That's what yeah, they look like cylinders. So what's going on in here is you've got these rolled up plates, like a Little Debbie, what are the things? A jelly roll. That's right. All right, and then I'll put this on the board in case we need to remember it. 8.85 times 10 to the minus 12th. And so we had this E naught before, but we had different units on it. It was like coulombs squared per Newton meters squared. And now we can replace those units with farads per meter. Okay. Okay, example 24.1. All right, I think you guys can handle this one without my assistance. It says the parallel plates of a 1 farad capacitor are 1 millimeter apart. What is their area? So I'll give you a few minutes to try this on your own, and then we'll show it as a class.